It's really great to meet everyone here. So my name is Anubrata. I'm just gonna try and share my slides quickly. Yeah. So my name is Anubrata Das. I am a fifth-year PhD student at the University of Texas at Austin. My research interest lies at the intersection of natural language processing and human-computer interaction. And evidently, explainability becomes a central part of using natural language processing for non-stakeholder use cases and high-stake use cases, which I'm going to talk about later today. This work that I'm going to present here is a paper that we published in ACL 2022 this year. We basically propose a new method for explaining natural language processing algorithms, especially for text classification tasks, with a new paradigm of like, how can we do this with case-based explanation for non-case-based reasoning applications, and how can we do that with modern NLP techniques. This work is done in collaboration with Chitra Gupta and Verilyn Kovachev, who's a postdoc at UT Austin, and my co-advisors, Dr. Matthew Lees and Dr. Jesse Lee. Yeah, so that's about it. And then I would please feel free to interrupt me and ask any questions if you have. I'd really like this to be as interactive as possible and have a discussion. So yeah, having said that, today I'm going to talk about a new explainable method, and we have our favorite Muppets in the age of natural language in the advanced natural language processing techniques. For example, BERT, and then we have GPT-3, and then so many other models. What happens with most of these advanced pre-trained language model is when you give it a, let's say for a classification task, give it an input, it can give you an output about whatever the task setup is. But most of the times we really don't know what happened under the hood for the model to make this decision. This is a schematics from DARPA XAI project from a few years back. And they kind of provide the context of how standard machine learning processes are leave users wanting for more. So for example, here we see that there is training data, there's the machine learning process, there's a learn function, and then there is a decision that goes to the user. But the user doesn't know why the model did certain things, why it did something else, why it did not do something else, when the model succeeds, when it fails. And also it becomes crucial in some other long-term questions, like when the model can be trusted. And if the model makes mistakes, can a user override that model decision or kind of understand that the model is making a mistake? And this is the XAI alternative of this pipeline, is where users will be satisfied by having all of these answers. And so when we put users at the center of these models, we need to have this kind of explainability. I want to reiterate that tasks that are complex for current models, for example, if you think about high-stake tasks such as hiring, or complex tasks such as content moderation, that kind of varies from geography to socio-political context and requires a lot of human review at this point. In these cases, why the model is wrong or whether the model is doing the right thing for the right reason becomes really crucial. So we have conventional methods that are interpretable in nature, like, for example, nearest neighbor, decision tree, logical regression. In these methods, we see that they're built-in explainability. But the issue is that these models don't work as well on natural language processing tasks per se. And so we lose out on performance, and these models are often not directly usable. On the other hand, we have seen this improvement in pre-trained large language models that has much better representation, and that leads to superior performances. But the key drawback there is that it's a black box model, and so we don't have the answers to the questions that we just discussed in the previous slides. Given this background, we propose this new method for explainability. So let's imagine the task here is identifying exaggerated framing in a sentence. So his ego is the size of Mount Rushmore, which is basically just saying that this person has a tend to have a really huge ego, and this can be said in different ways, and this is a example of exaggerated framing. So the model kind of predicts what the outcome is. It also identifies the training examples that are exaggerated framing and kind of closer in some latent sense to this test example. So your ticket furniture seems to be from Jurassic era, just to basically to indicate that it's very old. And so basically another example of exaggeration. And then you can see another one, the homework assignment will take years to finish. No homework assignment really takes years to finish, but this is an exaggerated framing of example of that exaggerated framing. So basically the form of explanation is the examples that the model has seen and seems similar to the input sentence. So this is basically an attempt to combine the best of both worlds, the powerful representations from the large language models and the case-based reasoning from from more traditional models such as k-nearest neighbor. In this case, we can achieve explainability and transparency by combining these two. And we show in this work that it's possible to do this without actually sacrificing any of the model performance accuracy, model accuracy for a particular downstream task. So the rest of the talk is organized as follows. First, I discuss the key idea of the prototype network that kind of builds the foundation of the model that we have built here. Then we discuss the model architecture and the training. We evaluate this on two different aspects. One is, of course, the predictive performance, because that's why we are building the model in the first place, and whether these explanations are actually useful. And I just conclude the talk by iterating through our key findings. So let's take a look at the key idea of prototype networks. This comes from computer vision. This is a paper from AAA 2018, where they introduced this idea of prototype network for computer vision tasks in particular. So what actually happens in prototype networks is you see this green and red dots. Let's imagine that's the data space we have for a classification task where red and green belongs to two different classes. So the prototype network learns to form soft clusters of these data points. And then you see this P1 and P2, they have the same dimensionality, or it's in the same latent space as this green and the red dots. And they are the cluster centroids, or the cluster heads for these soft clusters. And this is learned in an unsupervised manner. So there is no actual cluster label required, and they learn the latent clusters themselves through these prototypes. The inference is basically directly using these prototypes, very similar to k-nearest neighbor. I'll provide more details on how inference happens exactly for our work. But basically the idea is that whatever is closest to this cluster centroid gets assigned that particular class. Yes, Josh.
Yeah. So in the paper, what was the unsupervised clustering method that they used for this work?
The original paper?
Yeah, because you said unsupervised soft clustering method. So I was wondering what method that they use.
Sure. Yeah, I'll get to that in a second when I discuss the method as well. So I can share the details here. So the key idea of this prototype network, we could just take that off the shelf and apply it to a computer vision from computer vision tasks to a natural language processing task, but it doesn't really work very well. So we kind of play around with different techniques to see if we can match state of the art. Some of that means implementing transformer-based encoders, because those representations are really works well and state of the art right now. We have tried different normalizations of these distances, because the latent space matters based on how these clusters are learned, and how these prototypes are initialized, because that also kind of influences the quality of these learned clusters. And then we also try with a different, we have a novel interleaved training algorithm. I actually don't get into these details. You can check the paper for this particular details here in terms of what's the training algorithm and what are other things that we've tried to make this work for natural language processing. So let's take a look at the model architecture and training. And I think, Joshua, I think this should answer your question once I get through this part. So let's talk about inference first. We have a test instance, let's say, and we have an encoder that kind of performs it gives an word embedding from the test instance. And now we have these prototypes. And as I mentioned before, these are the soft clusters, P1, P2, and P-neg. So it's like all different prototypes with different classes, and there could be multiple prototypes with one class, within one class as well. So basically, once we have the encoded representation, the prototypes and the encoded representation have the same dimensionality. So we could actually identify the L2 distance between them. So once we calculate the distance of this encoded representation with respect to every prototypes, thus every clusters, we have a set of distances that we can feed to a linear layer. And once we have learned weights from this linear layer that takes this distance as an input, and we have we run that through a softmax function, and we get the prediction. Note that the only thing that we use for the prediction are the distance vectors, the distances themselves between the prototypes and the encoder, and not the encoded representation, which makes this model almost linear. Almost the inference part of this works as a linear model, and that makes it inherently faithful because whatever is the model using is what we use for explanations, and we'll see what that is in a second. So yeah, we look at the linear layer and softmax. So how do we actually explain, or how do we actually get those examples that are similar to the input test instance? So when we think about this linear layer, we have a set of weights from the linear layer. So when we take the distances and the linear layer combined, we can actually rank the prototypes in an order of importance by taking the multiplication between the distances and the weights. And when we have this order of importance, so we can rank these prototypes, we can retrieve for each prototype what's the closest example. Note that these prototypes are learned tensors on the latent space, so they are not sentences themselves. That's how we need to retrieve sentences, by just taking the Euclidean distance which is closest for that particular prototype. So that way we can actually find training examples that the model has seen before, given a particular test instance, just by using the distances and the linear layer weights. Any questions so far on inference and explanations?
I had a quick question. So you say the most influential prototypes using that formula or that product, is it ranked from highest to lowest? So like having a large distance would mean it's more influential, or you would want a small distance to a prototype, right?
It's inverse. Yeah, we would want the distance. Oh, sorry, that's a good question. Yes, no, we want the product to be highest.
If you want the product to be high, wouldn't you want the distance to be close to a certain prototype?
Yes. So what we want is that the distance to be closer and the weights to be higher. So yeah. So the detail here is that we actually take the inverse of the distance. So that's something that I've just missed out here. So the du and d2 that you're seeing, that's actually inverse. That's why that product is always higher.
Oh, I see. Okay.
But that's a good question. It's a little confusing here because you want the distance to be smaller, but then how d cross w is higher. I guess
okay,
that's what
so
you're asking.
the d1 is actually 1 over d1, whatever.
Yeah.
Okay, thank you.
Yeah.
I have a quick question.
Yes.
So I think this is probably something that you will get to later, but just at a high level, you talked about how using this linear layer on top of the distance makes this kind of architecture inherently interpretable. But is it really inherently interpretable if the encoder part is a black box, in that you don't know why the test instance is mapped to one prototype rather than another?
Yeah, no, sure. That's a great point. I think the argument I'm trying to make here is that given the representation, the rest part of the inference and the classification is interpretable. But yes, we still don't know how the encoder transforms into a vector space. And I don't think that like we have a lot of insights into how to tackle that problem yet in terms of how do we interpret embeddings directly, right? So my take on that would be that since the high-level representations works so well, and at least we have a one-on-one mapping between what the representation is and the sentence is.
Not necessarily
This is kind of the
one-to-one.
best we can do, given that using that is my sense. Sorry, go on.
It's not necessarily one-to-one because you could, in theory, have two different sentences mapping to the same embedding location.
Not really. I don't think that's true. Like they're not going to have the same vector if they're two different sentences.
Well, why? I mean, so yeah, go ahead.
No, I know what you're saying. That is there a theoretical guarantee that if there are two sentences that will give the same representation, but if we actually in practice take the embedding for each sentences, I don't think that they're going to result in the same vector, because the first thing is that they are in real space, right? Each of these numbers are real numbers, and then the dimension of this is very high. For example, in this case we did BART, which is like 1024. So if you have a combination of 1024 for each token, and then you look at a sentence, then that combination, it's really hard to, like, you know, in practice come up with two sentences that will lead to the exact same embedding, which is 1024 vector plus your sentence length. Does that make sense?
Yeah. I mean, I can see it mostly true empirically, but still, okay, yeah.
Yes. But yes, I mean, this is a limitation of how we even work in like natural language processing right now. So that's an excellent question, which I don't have answers to, like how can we actually interpret embeddings directly.
Sure, yeah, thank you.
Sure. Yeah, any other question before I move on to the training part? All right. So for the training, we have three different loss functions, and this gets to the answer of how do we learn the clusters. And so the first part is a cross entropy loss. This is basically looks at the classification label and looks at the cross entropy loss for getting that label correct or wrong. And then we have two prototype losses with two hyperparameters. So the prototype losses, basically what it tries to do is fine tune the embeddings and fine tune the prototypes and try to push them towards each other in the latent space. And this is achieved by two different interleaving losses. So which is basically for LP1, what we do is try to minimize the L2 distance between the prototype and the training example. So we freeze the training example encoder, and then we try to adjust the prototypes to reduce the L2 distance. And then we do the reverse, where we freeze the prototypes, and then we encourage the training examples to actually move close to the prototypes and form these soft clusters. So there is no explicit clustering objectives, as you may have seen in, for example, k-means or any other standard classification, clustering algorithms. In this case, what we actually just do is tell the prototypes to move closer to the encodings, and the encodings to move closer to at least one prototypes, and we see that like they kind of learn to separate themselves in a way where it works out for the classification output. Any question before I move on to the results on training?
So I have a quick question. So the prototypes are not really, so I might have missed this before, but the prototypes are tensors, and they're not really the sentences, right? So I mean,
yes.
are they're tensors, right? So
yes.
So as the output of the system, we can say that this prediction happened because we chose these prototypes, right? Is that the output of the system? And
yes.
How do you interpret that? So I tell you that this is that the question make sense?
Yeah, completely. Yes. So yes, I think this is the part that probably wasn't clear. So I'll try to reiterate this part. So once we have the prototype, we also retrieve the training example that are closest to each prototypes. So people, when we are giving this explanation to a user, we're not actually giving the tensors themselves and tell them that, like, interpret whatever this tensor is this. What we're doing is we're identifying training examples that are closest to the prototypes at the end of the training procedure, which is
okay.
yeah.
So your
more,
output is the actual training instances. Okay. Okay.
Yeah. Okay.
I have a question.
Yes.
So, okay, I understand what the explanations are. How do you choose prototypes? Are they randomly selected at first, and then you just kind of move points closer to these prototypes and then update the prototypes later?
Yeah, that's a good question. Yes. So we did try with random uniform sampling, and then we tried with Xavier initialization, basically, and that has worked the best so far. We are trying some of the semi-supervised clustering things right now, and kind of see that if we can, seed these prototypes with a little more intelligent set of examples instead of just giving blind, samples from Xavier distributions.
Mm-hmm. And also, how do you know the number of prototypes? Do you just make an assumption that it's one prototype per class?
Yeah, no, we determine that empirically because there is no one-on-one mapping as such. The clustering is unsupervised, so there is no label for these different clusters. So the idea is that whatever gives a good enough segregation for the examples, we just use that number. So we tried with different variations up to 100, and I think we got the best result around 20.
Interesting.
Okay.
So it's like so if I understand correctly, so you tried training like 100 networks with this architecture and then just saw what gave you the best performance. Is that how you chose the right number of prototypes?
Oh, I was saying that we tried a varied number of prototypes, including 100 prototypes is the highest we have gone to. Not 100 architectures, but one architecture with 100 prototypes.
But don't you need to retrain if you add in another prototype?
Yeah. It's empirically determined. So we trained like a bunch of different networks with different varied number of prototypes. Yes.
Okay, cool. I see.
Yeah. This is basically a hyperparameter. Like, how do you know how many layers do you need in your network, basically?
Seems tricky. Thanks.
One more question. So you have determined so there's a p negative, right? So does that mean, so what does that mean? So will it also tell us that these training samples are not related to this, not related to this example, or will that make a partition on the training samples, that because you will finally say that these training samples are responsible for this decision, right? And will this also say that it's not, these ones are not?
Yeah, that's a great point. So one use of this is kind of make some form of a counterfactual, where saying that these examples might seem similar, but they are actually not. But that's not what we did here. The diagram might be a little misleading because that's something that's in the paper where we write about. So if you recall the interleaving algorithm that we talked about, so what we do is we saw that an architecture where we dedicate a negative prototype for all the negative classes and then dedicate n-1 prototypes for the positive classes, that works much better than having all the prototypes to just figure out this classification by themselves. What I mean by this is that when we are training the prototypes, for one prototype, we just show it negative examples. It doesn't see positive examples like ever. And then for the other set of prototypes, we show it positive prototypes. And then we see that in that kind of training schemes, it works the best in terms of predictive performance. Yeah, the details of that is actually in the paper. I highly recommend you check out that algorithm that we have proposed there for training this.
Okay.
Yeah. Any more questions? Great. This is yeah. Thank you for all the questions. This is super interesting to have these discussions. Okay, so the task. So for evaluating this, we pick up this task for propaganda detection, and propaganda detection is this data set from EMLP 2019, where they propose identifying 18 different definitions, and then from this 18 different definitions, if somebody writes a particular sentence in one of these formats, like exaggeration, it's determined as propaganda. So there's a very complex prediction tasks. They had experts labeling this data, and detecting this kind of propaganda is very difficult for non-expert users because this relies on understanding what these different formats of propaganda is. For example, name calling or labeling or exaggeration, or comparing something with Hitler. These are some of the examples that are in this data set. So why we chose this task? Because it's a complex prediction task, and we wanted to see that if explanations are helpful for non-expert users, particularly who are not necessarily understands or have a background on understanding propaganda text online. So we reduce this 18 different techniques to a binary prediction task. So does a sentence contain a propaganda framing? So any of these particular type of framing will lead to a propaganda classification. Let's look at some of the examples of this propaganda. So Manchin says Democrats acted like babies at the State of the Union. So acted like babies, this is basically a framing that's very well known in propaganda, known as a name calling, where basically you are just attaching a particular name to a particular group of people. They can't even stomach being in the same room as the president. This is another form of like exaggeration, where basically they're saying they can't be in the same room as the president, which is probably not true. So given this propaganda detection task, we kind of try to figure out how well different baselines perform. So this is just majority class. We see get a 53 F1 score because it's an imbalanced, slightly imbalanced data set. Now, when we train BERT or take BERT, fine-tune BERT for this classification task, we get an F1 score of 73. Surprisingly, BART, which is encoder decoder version of this, it works slightly better for this particular task. Now, to compare with other baselines where we could potentially identify examples that are similar, we take BART representations and then feed it to a k-nearest neighbor algorithm on top of it. In that case, what we see is that the predictive performance is not as good. So we don't actually go into the understanding how good the explanations are, because we see that the predictive performance actually drops much lower. Our model matches BART performance with the added benefit of explanations. So fair, we have explanations and we have matched accuracy, but are these explanations actually useful? To understand that, we look at two different facets. One is model understanding. So does this explanation help users predict the model classification output? And the second part is explanation utility. So if there is a downstream task where non-expert users are trying to identify propaganda, giving these explanations, whether that gives enough signal for them to do this task better. To evaluate the explanations, we go back to this previous example setup. We have an input sentence, and then we have a set of explanations. We ask users to identify what the model may have predicted just by looking at these examples. Note that the labels of the examples are known to the users when that's shown to them, because that's basically from the training data. So in this case, we basically ask this question, given the example above, what do you think the model has predicted? For explanation utility, we ask a different question. What do you think is the correct label? So if you note that the key differences, the first one is about the model output. The second one is about the ground truth. In this explanation utility, we also try with two different groups. One group is shown the model prediction. The other group is does not see the model prediction. So we wanted to see that how much prediction alone versus prediction, how much explanations alone versus prediction plus explanations are helpful. So given this particular setup, we look at let's look at model understanding. So as a baseline, we randomly sample a bunch of examples from the training data and attach it to different test examples and ask users to identify what the model may have predicted. In most cases, the users don't know. And this is, by users, I mean Mechanical Turk users who are geographically limited within the United States. Most users don't have any idea when we give them random examples. And they either are incorrect in terms of identifying what the model has predicted, or reports that they don't know. Unfortunately, when the model is incorrect in its prediction, it's kind of the similar pattern where, so the explanations are not very useful for people to understand what the model may have predicted when the model had made a mistake. And when the model is correct, in that case, we see that reverses. So the explanations are much more helpful in terms of understanding what the model is doing when the explanations are correct. That actually gives an interesting signal that if we're trying to train people to understand what might be happening in a model, we might want to train them using the correct cases first before they go on to identifying incorrect cases. Having said that, future work actually needs to kind of examine this particular phenomenon. When the model is wrong, how can we provide enough signal so that people can understand when to override that?
Hey, quick question.
Yes.
So if you go back to the slide, the second and third group, where the model makes incorrect versus correct predictions, looks like basically mirror of each other. So does that mean that the user basically defaults to the model prediction in all cases?
Yeah, that's a great observation, actually. So one of the artifacts that we have seen with doing explanation studies with people on Mechanical Turk, like we have seen this in previous studies as well, that there is a tendency of people just blindly following model prediction. And to alleviate that, if you remember this setup of model understanding, people don't actually look at people don't know what the model has predicted in this case. All they see are the explanations only. So if I go back a couple of slides, this is the setup. The prediction is hidden.
So
and we actually,
the user basically predicts the label in those three examples.
The user basically predicts what the model output would be given those three examples.
And that model and the user's prediction of model's prediction could be correct or incorrect with respect to the ground truth, and that is what you're measuring.
Yes.
So in that case, in what sense is the explanation helping with the task? Because
this is not the result for helping with the task. This is just whether people can form a mental model of whether the model has gotten things correct or not. So you can think about like whether users are able to simulate model behavior without knowing what's happening under the hood.
I see. So, but then it looks like the very easy way to quote unquote cheat this task is just to provide the most representative positive versus negative example in all cases back to the model's prediction.
Yeah, for sure. So and I don't necessarily think that that's a bad thing, because if the model has actually identified the most representative labels from these samples, then the model is actually learning that labels pretty well, right? So even if that is how people have arrived at a correct answer, I think that gives us them enough signal that, oh, we want to look at the training examples and see that what their labels are, and that's where what the similarities for those labels are. Does that make sense?
Yeah, but I mean, people, it's basically like saying just giving the model prediction away with those explanations, but it's not clear how those explanations are generated. That's like my earlier question of like, it's not clear how that embedding vectors are generated. I guess.
Oh, like, yeah, sure. Yeah, I mean, that definitely gets to that limitations of I mean, does this mean that people can interpret how embedding algorithms works within transformers? I don't think so, but that's not the problem that we're trying to solve here. What we're trying to solve is that when people are actually deploying these models in real life, and we are doing that without even having solved that transformer problem, like people work on different problems for informing understanding transformers better, for example, mechanistic interpretability, right? How transformers are actually arriving at different decision-making processes. And that problem is probably going to take longer to solve, but we have these models in deployment already where people are using this model there in their tasks.
Sure.
So what I'm operating is at that task level, that without trying to solve that transformer problem, can we do something where it gives enough signal so that people understand what's going on to some extent. Yeah,
that makes sense. Yeah. Thank you.
Sure.
So does it like similar to the simultaneity evaluation criteria that so that's the, I think the Bonsall and Hayes paper that has Hayes and Bonsall, but so you can, I think I can share the link with this. So it does look like that.
Yeah, yes, we did cite Hayes and Bonsall for this. This is basically simultaneity. So yeah, in the paper we cite Hayes and Bonsall and how we use how we take the inspiration for evaluation from simultaneity there. Yeah, thanks for the point. Okay, so moving on to the downstream task where we have explanation utility. So in this case, we show the users just the sentence. So if you imagine that the annotation task is, here is what defines something to be propaganda. Here are some examples, and here's a sentence. Identify whether this is propaganda or not. That's the sentence only case. And then we have sentence plus random examples. So we kind of take random examples from the training set and attach it onto the sentence by saying that these are similar. And of course, that fools the users more, as someone correctly pointed out just a few minutes back, that if you just look at the label and random examples, kind of throws off that cheating game a little bit. And then we look at different varying model performance in across different cases and see how that might inform that compares with the user accuracy. So just to clarify this x-axis a little more, the 50% is the case where we basically do that post hoc. So at a training, when we are providing these examples, we sample these examples so that the model accuracy comes to 50% based on the sample that people have looked at. And the 75 is highlighted here because that's where our model is at right now. And then we wanted to see what the upper bound looks like. So that's why we give all the correct cases. So the first case where we just show the explanations to the users and not the model prediction, in that case, it performs better than random at a 50% level, but that's not really that impressive. And then we look at the 75% case where we just provide the explanations. We see that it's better, much better than the 50% case, but it's still worse than sentence only, which is a little weird and interesting. So basically, we see that explanation utility increases with the model performance, but explanations alone are not super helpful to do better, at least for this task, even if you just give the sentences to people. And then to see the upper bound, that does it ever get better? It does get better with model accuracy, but just slightly. But when we add back the prediction, we see that the prediction and explanations together are much stronger signal. And this could be an artifact of people blindly following the prediction outcome. And that's why we kind of present explanation utility and understanding together. And when we look at a 75%, this is the first time we see that we have we overcome the baseline of just the sentence only cases. So if you provide predictions and explanations together, people perform a little better than the sentence only cases. And we see that this difference actually gets much higher as we go higher up in the performance cases. I can't empirically say that how much this is gonna get better, but we see that there is a increasing trend when we have better model performance. So just looking at this graph, what we can say is that explanations alone are less helpful than explanations along with the predictions for this downstream task cases. And then we see that this kind of increases with better model accuracy, but really doesn't do a lot better than this explanation, than some of the baselines. So at the end of I'm at the end of the talk. So the conclusions are basically, we introduce a novel method for training example-based faithful explanations. We have a model that matches predictive performance with added benefits of explanations. We show that human evaluation is kind of a mixed result here. We see that explanations are helpful in forming model understanding, but that's only when the model is correct, that signal is strong enough. And then we see that it's improving user accuracy on the downstream task for propaganda detection. The paper is available on arXiv and ACL Anthology. The code is also available on GitHub if anybody is interested. So once again, thank you everyone for your time, listening to me and asking wonderful questions. I would just quickly like to mention my funders. Good Systems is a UTEX initiative that has been funding my PhD. Knight Foundation, Micron Foundation, Wipro, and National Science Foundation have also funded it at different stages. And Texas Advanced Computing Center helped me with the resources for conducting these experiments and learning, running those large models online. I'm on Twitter, and so please reach out, or my email is also on my website if you want to also discuss offline. So thank you so much.